My name is Alex Terenin, and today I will tell you about non-Euclidean Matérn Gaussian processes. This work is largely work from my PhD thesis, specifically sort of the second half of it. And so I'm really excited to share that with you. That thesis was at Imperial College, and I'm now a postdoc at the University of Cambridge. So to tell you about non-Euclidean Matérn Gaussian processes, I first need to tell you about Gaussian processes. And so Gaussian processes, really the way to think about that is it's a method for interpolating data with the structure of probability built into it. So in particular, we have here a scatter plot of data on the x-axis, and we also have some y values, and we want to interpolate between the x and the y values. So sort of a very standard regression problem. There's a very easy way to transform these kind of things into classification problems, kind of work in that setting too. But the key thing that we're doing different from usual empirical risk minimization is we're doing Bayesian. And so what that means is that instead of just minimizing some loss and getting the learned function out that way, I'm going to be doing that using conditional probability. And that in particular gives me these error bars, which you can see kind of grow a little bit as you move away from the data. On this slide, there's sort of not a lot of variability, so they're quite small. But the important thing is that I get them, A, and they are the conditional probability distribution of the function given the data. And so that was the video that you saw at the beginning, which was the algorithm that calculates that thing, sort of starting from the prior and then shrinking the error bars from the prior to get the posterior. Now, why do we care about such a thing? One reason why you would want to do learning in that way in the first place is because if you have the structure of probability on your learned model, you can build the decision theoretic structure on top of it and do things like Bayesian optimization. So in Bayesian optimization, we're going to use the object I just showed you to construct a black box optimization algorithm. And the goal is minimizing some unknown function phi, which what we're allowed to do is we're allowed to evaluate it pointwise and get a pair of x, y values. And that's the only thing that we can do. And we want to do that sort of as quickly as possible. And for purposes, at least of this slide, I'm going to assume that the phi is a function from some kind of closed interval or cube into the reals. I could do that more generally, but there's no reason to for illustrative purposes.
You want to move just the chapter bit so that you can see?
Yes, I'm going to do that and do that. Is that I hope is better. Sorry about this. So the way that we're going to do that minimization is we're going to take the x-y pairs that we saw. We're going to build a posterior distribution. And if there is no data, then you stay with the prior distribution. And again, using the data consisting of the x values and the evaluations of the unknown function. And after we've done that, then the question is, where do we go next to gather more data? And the answer is, well, that's why we kind of bothered to build the structure of probability into the problem in the first place, which is once you have it, then an idea is to select the next data point as the optimum value of some function alpha, depending on the previous data, where alpha is called the acquisition function given the data set up to time n. And so there's a whole literature on exactly how to construct these things. And I'm going to show you an initial example, which is Thompson sampling. Now, Thompson sampling is a random acquisition function. It's not a deterministic one. You can have deterministic ones like the expected improvement, but I'm not going to talk about those. And the random acquisition function is very simple. You literally draw a function from the posterior distribution. Again, the posterior distribution is this Gaussian process, this distribution over functions or over curves. So you draw a random curve from there, and that thing is now deterministic because you've drawn it. And you just take the minimum value of that. And so that's an acquisition function. It turns out actually to be a very good one in the sense that you can prove all kinds of bounds on how good it is, in a sense that I'm sort of not going to talk much about because it's a different topic. But it turns out that this is a very good idea, at least in this setting. And the reason why is because it balances the kind of decision theoretic, reinforcement learning theoretic explore, exploit trade-off that occurs in this problem. And the reason you have such a trade-off is because you don't know the function. So because you don't know it, you have to balance taking advantage of points that you know are good and close to the minima with other things you haven't seen yet because you don't have data in that area. And so this is why it's interesting to actually study Gaussian processes from a kind of, again, interactive decision-making, active learning, reinforcement learning bandits kind of setting. Because if you have a Gaussian process, then you at least have a sensible way to design these things, which is not at all true in general. And the setting is much better understood. So let's just go through what this might look like. So I'm gonna have and right now I don't have any data. So my posterior is just the prior. And the prior, what I'm showing here is the upper and lower 95%, I believe it might be 99% error bars for the function. And so this dashed line here is the function we're going to minimize, but we don't know it. So right now that's not incorporated into the posterior because it's just the prior. And the blue line is one random curve drawn from the prior, whose minima happens to be at this point. So this like cross is going to be the minima. And so this point right here is going to be where we're going to evaluate data. Now, we don't have any data, so any point's as good as any other point. So we evaluate there. It turns out that's not as good as we thought. And so what do? Well, we draw another curve from this time the posterior given the one data point, and we think it's minima. Right there. And I mean, we can see that when we evaluate it, it's not going to be there. It's actually going to be up there. But now it picks a different minima over here. And so we evaluate that. And now all of a sudden, the model is much more interested in trying out data points sort of nearby here. And the reason it does that is because it knows that in the distance from here to here, eventually it's going to probably try something in this region, but it's probably not going to be trying stuff over there just because it can already estimate based on the data that the function is smooth enough that there's no sense in doing that. It should probably focus most of its attention sort of in this region here. And this particular one happens to be quite close to the previous evaluation, but that's fine because the previous evaluation is quite good. So this is Bayesian optimization, and it works well, both in theory and in practice. And so that's one thing that I showed you that you could do with the Gaussian process if you had it kind of as a technical primitive. And another thing you can do is this time a different setting, we're not doing optimization anymore, is you can model the motion of dynamical systems from data with uncertainty. And so here we have a pendulum, and we've observed some trajectories of it and trained a Gaussian process model to model its equations of motion, which we're pretending we don't know. And if you're doing robotics, you might not know because you might be modeling an object that's not part of the robot and you couldn't have designed ahead of time. And so if we take a starting point x0, which is in red, and we time step the system forward using just your standard time stepping regime, then what you see is the further forward you go, sort of the more error you have, but not completely. Because at certain times here you have a little bit less error, simply because it's not moving as fast at those times. And so building sort of a model in this way and taking into account the propagating uncertainty is sort of a fairly sensible way to deal at least with simple systems like this. Maybe there's another thing to be said about more complicated systems and sort of expressive capacities and such. but at least this is something that one can do. And so now I want to sort of shift a little bit and say that in robotics, some of the problems that people face in practice, they're like the ones I just showed you. But they're not exactly the ones I showed you. As an example, if you're interested in using Bayesian optimization to determine the optimal orientation for your robotic arm at a certain time point, based off of some process you have for doing that, whatever it is, the x-axis from which your inputs lie is not going to be the real line, and it's not going to be a cube. It's going to be a sphere. Similarly, if you talk about manipulability ellipsoids, and I have no idea actually what that is. This is something my roboticist collaborators know about. But if you want to optimize a manipulability ellipsoid for some purpose, that's going to lie on the manifold of symmetric positive definite matrices. It's also not going to be the real line. And in some sense, the structure of it is, if you want to take into account sort of the right geometric structure of the problem, it's actually a little bit maybe even more complicated than something like the sphere. And yet another case is joint posture, which is rotational and therefore lives on the torus. And so what we're going to be talking about in this talk actually mostly is going to be about how do we adapt Gaussian processes as a technical tool, which I just showed you is sort of a useful building block for kind of upstream methods. How do we adapt that to the setting where the data you're gathering is going to have this geometry as part of its structure? And we're going to study that question for the remainder of the talk, which brings us to geometry-aware Gaussian processes. So first, to make this sort of a little bit concrete, I should first tell you about what kind of model, Gaussian process models, people are using in the Euclidean setting. And the most popular of those is the Matérn class, which for varying degrees of smoothness, some random samples from the prior are shown here. So in particular, there's a parameter mu, which allows me to sort of control how the amount of differentiability that your prior has. And the formula for this thing is sort of this terrifying looking thing, which I don't suggest you focus on, other than to note that the hyperparameters here are sigma squared, which is variance, kappa, which is the length scale, and the length scale sort of has to do with how quickly things decay, or how quickly things sort of lose dependence as you move further and further away, and the smoothness, which I just told you about. Now, if you take the limit of this thing as the parameter nu controlling the smoothness goes to infinity, then you recover this thing, which is the squared exponential kernel, sort of a little bit nicer looking. Maybe I should have shown that one first, just so I don't terrify all of you. And so the question is, how can we adapt a notion similar to the one that I just showed you, the Matérn class, to the setting where the data lives on a Riemannian manifold, here being the torus and the sphere, which again, I just showed you actually occurs in practice in robotics and in actually many other settings too. And so that's the question that we're going to ask, which is how do we generalize the Matérn model class through its covariance function, or the kernel, which is a bivariate function that describes kind of how much nearby things depend on each other. How do we generalize that to this setting? And the first thing you might try to do is sort of start with the squared exponential version, a little bit simpler, and replace the Euclidean distance with the Riemannian geodesic distance, at least assuming you have it and it's, your manifold is nice enough to talk about such a thing. And it doesn't work, actually. There's a theorem by Fragen et al., which basically says that if that expression is positive semi-definite, which it must be in order to define a valid Gaussian process mathematically, then the manifold is isometric to a Euclidean space. I mean, that's a disaster. That means we can't even talk about things with curvature if we use that formula. And so you could sort of wiggle around this and say, well, the problem really happens if this parameter, if the length scale is too large, and so you start having like an effective topology, and you can sort and it's not the fact that you have mathematical issues does not stop people from actually using this in sort of applied robotics papers. So the big lesson that we're going to take from this is that we abandon the geodesic distance as an idea. Even though it looks intuitive, it looks appealing, it's not the right notion. And so we need a different candidate generalization, which means we have to go back to our Matérn process and look for a different point of view that we can adopt. And that point of view is going to be that of stochastic partial differential equations. So here, what I'm showing you is an equation that the prior satisfies, where in this equation, the nu kappa is one of the smoothness in a length scale. E is the dimension. I'm kind of suppressing the variance of this thing, which is something that you can calculate, and it makes the whole thing a lot uglier. So I don't know if you don't want to learn it. You just divide by the sort of variance of the thing to normalize it. And in this expression, the delta symbol denotes the Laplace operator, which is the trace of the Hessian, or the sum of the second partial derivatives of the function. And script W is something called the white noise process. And I'm not going to tell you what that is because it's a little bit complicated. But I will tell you that there is such a thing, and it's sort of something that's kind of similar to IID Gaussian at every point in space, but it's not quite that, because if it was that, you couldn't integrate it, so you have to do a bit of analysis. And so if you want to know more about that, feel free to ask me at the end. But the reason I want to talk about this idea is because this class of equations generalizes very well to the Riemannian setting. I mean, it's almost immediate. All you do is replace this guy with the Laplacian on your manifold, replace that guy with the white noise that comes from the Riemannian sort of volume form, which comes from the metric. And again, I wave my hands about like exactly what this guy is a little bit, but suffice to say, if you kind of know how it's defined, then it's immediate to bring it to the Riemannian setting. And I also want to say that this idea originally was due to Peter Whittle in the 1960s, sort of the pure mathematics community. He also did quite a bit of statistical work, not so much with this model, but with things like point processes. And Finn Lindgren and Håvard Rüge, who reintroduced this 50 years later in the statistics literature.
Can you explain a bit more just how the Matérn kernel is related to
the Matérn kernel is exactly the covariance of this. So if you take that equation, you solve it, you get a Gaussian process, and you ask yourself, what's the covariance of this process? It's exactly the one that I just showed. So all that, in other words, all that this is just a different way of looking at the same prior that we have. So we haven't changed the prior, at least not on RD. Yep. Yeah, basically. So F is the thing you want to know, and this thing here is the linear map between spaces of functions, and this guy, I think of sort of as like the functions. It's exactly like a partial differential equation, kind of like the heat equation or something else, with the one caveat that there's no notion of time in this model, which there often is in PDEs. So this guy has a name. It's called the heat semicolon. This equation is sort of the limit of this equation in a sort of suitable sense. And the reason I write this one down is because I showed you the squared exponential kernel. Well, the Matérn satisfies this guy, and the squared exponential satisfies that equation. And I should also tell you what in the world I mean by taking e to the power of the Laplacian. What I mean is take the Laplacian, take its eigenvalues, take e to the power of those, and then rebuild using the same eigenvectors. That's also what I mean by taking this to the power of here. in the case that that's not an integer. If it is integer, it coincides with the naive notion. So here's the magic formula. What we prove in our work is that the covariance of the Riemannian Matérn Gaussian processes, which again I've taken to be defined by those equations with all the components replaced by the Riemannian analogs, prove in our paper that the expression for the covariance kernel is just this. And what's going on here? So we have our kind of variance. We have a certain constant that you can calculate sort of what it is if it kind of matters to you. This is for normalizing the variance. There's this expression which looks a lot like the differential operator we just saw. To the power, which is the same power, but you lost a factor of 2. And you have these guys here, which are the eigenfunctions of the Laplacian operator. So in other words, these are the Laplacian eigenvalues. That's the Laplacian eigenfunctions. And if you know those, then you know the kernel. So in particular, if you're working on the circle, the sphere, sort of manifolds where these things are, understood well enough, this thing is analytic up to, some truncation level. In fact, the expression I've shown you here is exactly the expression for manifold Fourier features, if you know about Fourier features. I'll talk a little bit about them later. So what does this thing look like? Does it even look similar to the Euclidean ones, which sort of decay smoothly and have other good properties? Well, it does. On the torus, it sort of looks like that. Sort of the further away you move, the less dependence you have. And very similar on the sphere. And for kind of illustrative sake, we also have a dragon manifold, which is a very non-Euclidean space. And so here we're showing the return 1/2 kernel from sort of a point that we choose. And we see that the kernel adapts to the geometry of the manifold. So the Gaussian process sort of is actually adapted to it in a very, at least to us, intuitive looking way. Note again that these things in general are not based off of geodesics. It turns out for the sphere they are, using a much more complicated looking expression than the squared exponential of the geodesic. It's sort of a huge thing that you get, but this one does only depend on distances in kind of a very non-trivial way. That one doesn't. You need more than just the geodesics to get dependence on the torus. Actually, it depends on the individual distances along the axes of the torus. So you need to know sort of the distance around and the distance this way. So let's just see like what this looks like on the dragon manifold. So if we have a ground truth function that looks like this, that's the color, and the black is where we're going to have data. Then we train the model, we get that posterior mean, which is quite sensible looking. It is, it sort of shrinks to the fire up in this horn area where there's not very much data, and near the snout. But I think the really interesting plot is if you look at the standard deviation, and it's a little bit small, but what you can see is that if you take these points and you sort of move away from them, then the uncertainty increases both locally and globally in a way that is adapted to the manifold's geometry. And so what this shows us is these kernels behave exactly in the way we kind of hoped they would, at least empirically. Now you can also see by drawing some random samples from the posterior that you get samples that look sort of similar to the ground truth. In fact, this sample looks closer to the ground truth than the mean does sort of near the legs, just because it's, I don't know, more lucky in that sample. And so you can do things like Thompson sampling in this kind of setting with these ideas. So that was what I wanted to tell you about GPs on Riemannian manifolds. What I want to do now is sort of tell you, once you have that model class, the question we ask is, what else can we do with this? And one thing that we can consider is the notion of a weighted undirected graph. So a graph is just a collection of nodes, and there's some edges between the nodes. And what we're going to consider is functions from the graph into the real numbers, where the goal is to take into account the structure of the graph. So in particular, the function is going to take a single node on there and assign a number to each node. And we can do this for different nodes. And what are we going to do in this setting, which is another setting where it's sort of not completely obvious how to define kernels. There's certainly some kernels out there, but what we're going to do is we're going to take these same equations we started with that I showed you previously. And what we're going to do is we're going to replace both the white noise and the Laplacian with the graph analog. Now, the white noise on a graph, I'll tell you exactly what it is. IID Gaussian at the nodes. Maybe you do some rescaling based on the weights of the graph if you kind of want to, deal with that. But at least if all your weights are the same, then it's IID at the nodes. So that's kind of easy. And the Laplacian, turns out the expression for the graph Laplacian is at least up to a minus sign, is just this, where you take a node on the graph and you subtract all the neighboring nodes and you multiply them by the weights and you just sum this thing. So it's kind of exactly the discrete sort of derivatives. Now you can express this as a difference between the degree matrix of the graph and the weight matrix, or the weighted adjacency matrix. And something I emphasize is in graph theory, people use a different sign convention. So this thing I've shown you is actually the same thing as minus the Euclidean or the Riemannian Matérn kind of, because you have two different groups of people that study those problems and they choose different ways of writing those things down. So in particular, the Graph Matérn class is just this. You take your standard IID Gaussian, you take your Graph Laplacian, and you can write down kind of these expressions. Now this is really simple at this point. It's just a matrix. And that's just the random vector. So you multiply the matrix to the other side, because it turns out those things are nice and invertible, at least in the settings we look at. And again, the expressions here are based off of taking the matrix, eigenvalue factorize it, apply this function to the eigenvalues, and then rebuild it with the same eigenvectors. So that's the idea we use. The name for this is called functional calculus. So we just get a bunch of multivariate Gaussians that look like this. Now, you could have just put a multivariate Gaussian, I don't know, IID Gaussian in all the nodes of your graph without taking into account any of its structure. But then you would get a graph Gaussian process that kind of ignores the structure of the graph. And that's maybe not what you want for using these things. And similarly, again, just like previously, we get a formula for the kernel based off of the eigenvalues and basically shifted powers of the eigenvalues and the eigenfunction. So this is just another way of rewriting the eigenvalue factorization of such a Gaussian in a way that makes it clear that the expression we've written down is what's called a graph Fourier feature expansion. And Fourier features are kind of a long study topic in Gaussian processes, where again, here lambda n and fn are the eigenvalues and the eigenvectors of the graph Laplacian. So what do these things look like? Well, you take some graphs and you compute the prior variance, and the first thing you notice is the prior variance is not uniform for these models. And that's completely different from the Euclidean setting. Instead, it sort of depends on the geometry in a way that's complicated. It's something sort of, it's not really just how many neighbors a node has or something like this. It's more like something more similar in spirit to how long it takes a random walk to return to, things like this. I don't have a formal statement for that, by the way. It's just kind of empirically, roughly what we've seen. But the key message here is that in these models, the prior variance depends on the geometry. And so what can we use this kind of thing for? Well, we can do interpolation in spaces where it's not even necessarily obvious how to do interpolation, like otherwise. So here we have this problem where we have a traffic system with you have sensors on all the roads and people drive around, and we have a mean and a standard deviation, and you can see that so the nodes with the white dots are ones with sensors, and the ones with no white dots have no sensors. And so you can see that you have much higher variance in regions where there's no sensors, or in regions where there's like, I don't know, a lot of just different variability on the same road. I don't know, maybe there's like some kind of accidents there that day, and people are driving slow at one point, then they speed up after they pass it. And the cool thing is here is that you can look at this at different scales. So if you zoom in, then what you find is that the interpolation process really takes into account like the structure in a way that is like very different from the sort of distance. So here you can see that you have very different kind of predictions on one side because you have traffic in one direction of the road, but you don't have it in the other direction. And the individual sides of the road are represented by different nodes and edges of the graph, which even though they're close in Euclidean space, they're far away like in graph distance. So what this tells us is kind of that this model class shares some of the same properties in this setting that it did of the original Euclidean model class that we started with. Now, what's the relationship between the two models I just showed you? Well, roughly speaking, if you take your manifold of a sphere, replace it with an isosceletron, and take bigger and bigger isosceletron, well, you get the right thing in the limit. And this takes some work to make precise, but in our paper, we have links to people who study essentially the same question in like a sort of mathematics setting rather than machine learning setting. So, but statements about this are available in the literature by translating those results appropriately. Yeah, you have to do some work to like understand exactly what it means to prove such a thing mathematically, because you have to define all the notions and the meshes and all this stuff. But it turns out that people have studied this just for SPDs generally. So it's, once we make the connection with those models, then it's reasonably clear like what these things look like. But we don't do this analysis in our paper. Yeah, exactly. That's exactly where this kind of, these kind of things come from, is for motivations in communities like that, especially if you're talking about a physical system with noise in it. And so, but by connecting the Gaussian process model class to SPDs, we get access to essentially all of those ideas, which are well studied, coming from very different motivations. So yeah, that's right. And so I'm just looking at the time. I do still have time. I'm sorry if it's been a little bit quick. The next thing that I want to briefly show you about, and I'm not going to show you in a lot of detail, I'm only a little bit of detail, a little bit less than the previous stuff, is vector fields. So it's another, again, natural question to ask in a setting like this, which is, can you model vector value data instead of scalar value data on vector? And so here we have some spheres with vector fields on them. And in particular, one thing that's true, and it's true because all of these are smooth vector fields, is that they will vanish always at least one point. And the reason for this is by sort of standard theory, it's not possible to have a smooth, non-vanishing vector field on a sphere, at least in R3. And that's a theory. It's kind of called the hairy ball theory, because you have a ball and you have some hair growing out of the ball, and you take a comb and you try to comb the hair. There's always going to be a cowlick or a swirl like somewhere on the ball. Unavoidable. And you could try to make one and play around with this and convince yourself. But because you have such properties of these things, then mathematically they're sort of a little bit more structured than Euclidean vector fields. So then the question is, how do we deal with that with Gaussian processes? And so in this setting, there's even less hope of getting kind of an analytic expression for the kernel without some kind of mathematical machinery to tell you what it needs to be. And so in particular, yet another issue is that if you want to represent a vector field numerically, then one thing you can do is you can start with some scalar fields or some just scalar value functions on a manifold, and then multiply them by this thing called a frame, which the frame kind of tells you which direction the scalars should point everywhere. That thing, by the way, has to be discontinuous. But if we're working with meshes, that's okay. We can kind of deal with that. But if you define a vector field in this way, then it's extremely important that if you choose a different frame, then you understand how to transform these guys into these guys so that both of these things yield the same thing. And you get one vector field irrespective of the exact choice you made with how to kind of represent it numerically. And so that's a basic consistency property, which if you don't have, you can't really call the thing you have like a proper vector field. And so what are we going to do? Well, we're going to figure out how to deal with issues like this. And the way that we do that is via the following trick. So the idea is going to be to take some scalar fields defined on the manifold. And if the manifold can be embedded into three-dimensional space, so we're going to use an embedding, largely because it's computationally quite convenient to work with them. They're not nice for proving theory, but they are nice for compute. And we're going to take these three scalar fields and just build a non-tangential vector field. So a vector field can fly off the manifold and go somewhere else. And you embed the manifold in a higher dimension so you can do such a thing. And then the last thing we do is we just take this thing and flatten it onto the manifold by projecting it down. And so in the paper there, what we do is develop the mathematical machinery needed to make that idea precise. It's a very simple idea. We call this class the projected kernel class. And it turns out that all kernels are projected kernels, sort of with an appropriate choice of an embedding and an underlying scalar field. So you don't lose any expressivity by doing this. And again, the idea here is that we construct our vector fields as, Gaussian vector fields in a suitable sense of what that means by taking some scalar fields. Here's three of them, sticking them into R3. So you get a map from the sphere into R3. And the sphere lives in R3, so you just take the R3 output and flatten it, and that preserves Gaussianity. Maybe not completely obvious, but we show it. And so the final thing that I want to sort of mention is the idea of just bringing these things back to Bayesian optimization, which is the thing that we started with in the first place. So if we do geometry-based aware Bayesian optimization by using these models in a Bayesian optimization loop, does this help? And so what we do is we introduce some benchmark functions. That's the Ackley, Levy, and the Rosenblatt function. And they kind of have different features, like a lot of local variability, a lot of kind of different variability in different directions, kind of all these characteristics that make them difficult to optimize, especially with gradient descent. And what we're going to do is we're going to take these things, which I've shown them to you in 2 dimensions, but you can define them in higher dimensions. And we're going to restrict them onto the surface of a manifold. So for instance, we consider the sphere and we restrict that thing onto the surface of the sphere, where we kind of shift it around a little bit and such to make sure that restriction sort of behaves in a sensible way. And then, you have a unique optimum and such, similar to these. And we're going to do Bayesian optimization. And so for the Ackley function and 3 different manifolds, the 3-dimensional sphere, 5-dimensional sphere, and the special orthogonal group. So the special orthogonal group you should sort of think of as a space of rotations, roughly. It's the results we get, where in this setting, you can see that for the 3-dimensional sphere, sort of Euclidean versus Riemannian, quite similar performance, and sort of a lot of variability. So this one is sort of a little bit too low dimensional for, at least with the Ackley function, to sort of make a big difference. But if you move to a 5-dimensional sphere, that's not at all the case. Here it makes a very big difference using the Riemannian model, much better performance than the Euclidean model. And essentially because it's sort of the topology starts to play more of a role in the structure of that function. And for the special orthogonal group, you kind of get something in between those things, at least for that function. But then if we look at the Levy function, and I apologize, it seems the labels of the manifolds vanished somehow from the previous picture of this one. I'll fix that in the slides I put on my page. For this one, what we find actually is, again, the same thing for the 5-sphere topology sort of matters quite a bit more. But we also find that the Matérn model here is a much better model than the squared exponential model. So having the flexibility to include smoothness as a hyperparameter, which is the case for our kernels, but maybe not the case for other kernels, actually makes a big difference in this example. Yep.
Standard square extension.
It's with the Euclidean distance on a higher dimensional space. So in other words, you take your 2-dimensional sphere, you embed it into R3, and you consider the diagonal distance that kind of goes not on the manifold, but through the manifold, and the higher dimensional analog of this. Now, the problem there is, you have to deal with how do you optimize those things, because the minimum of that Gaussian process might not lie on the surface. You have to do constrained optimization, and you have all these issues that basically arise from that in practice. So it's a little bit more messy to deal with, but people have used these things, so the machinery to deal with it is sort of there. But yeah, basically. So that's the Levy function. And then we look at the Rosenbrock function and we find that everything performs sort of very similar on that one. So topology seems to play a very little role, and the same for smoothness. The Rosenbrock function, again, is this one with this banana-shaped thing where sort of all methods perform similarly because it's kind of doesn't have enough structure. And so the takeaway from these results is, well, it's really good to have a tool like this available, because if you have a problem that demands it, then it probably performs much better. And then if you have an easy problem, maybe you don't need it. But at least you have the capacity to use such a thing, rather than if the tool was never even there. So that's kind of the takeaway from these slides. And yeah, with that said, I'm happy to take any further questions or explain stuff. And I just want to say thanks very much for listening. Here's my page. I'm also on Twitter, so you can find me there. And all the citations for the bits and pieces of work that made all of this possible over the last couple of years. So thank you.